Once again, I welcome in the course Irrigation Engineering. So in the last class, I have discussed or I have started the canal design, and in canal design, uh, firstly I will discuss the what is sediment transport and then mechanism of the sediment transport. And then I have discussed the condition for no sediment transport either from the channel's bed and channel side slope. And then we have solved problem based on this. So today I will start the new topic, that is design of stable channel in India. And in design of stable channel, firstly I will discuss what is stable channel or regime channel, what is the condition of the regime channel, and then I will discuss the hypothetical theories for the design of alluvial channel in India, that is Kennedy theory, and after that I will discuss the Lacey's theory. So I am going to discuss the design of stable channel. So firstly, generally we use the design of channel. So in design of channel, generally we use the Chezy's equation or Manning's equation. But this Chezy's equation and Manning's equation is used for the rigid boundary channel, in which the shear stress is less than the critical shear stress. In India, alluvial channels are designed on the basis of hypothetical theories given by Kennedy and Lacey. So today I will discuss the Kennedy's theory, and later class I will discuss the Lacey-Silt theory. So the channel in which neither silting or scouring take place, such type of channel is called stable channel or regime channel. So firstly I am going to write the definition of the regime channels. So the channel in which the channel in which neither silting nor scouring takes place. But in actual, it is not possible uh, that in any channel neither silting or nor scouring takes place. So what is regime condition? So regime condition, there are various conditions. The first one is the channel should flow uniform. So flow should be uniform, and the second one is the discharge should be constant, and silt grade and silt charge should be constant. Silt grade means their size should be same, and the silt charge means the quantity of the quantity of the silt in any channel will be constant. So I am going to discuss the Kennedy's theory. This theory was given by R.G. Kennedy, an executive engineer in uh, uh, Punjab PWD, and this theory was given in 1895, and for the upper Bari Doab Canal system. So according to Kennedy's theory, according to Kennedy's theory, he has given the expression of critical velocity V naught is equal to a y to the power b. This expression was given by Kennedy for upper Bari Doab Canal system. Here V naught is the critical velocity. V naught is the critical velocity. A and B are constant, and the value of A is 0.55 and the value of B is 0.64. This constant depends on silt charges. And this equation is valid for the upper body Dwarf canal system only. So Kennedy's theory given the expression of critical velocity. V naught is the critical velocity, and this theory is applicable for the upper body Dwarf canal system. But for the for other canal, Kennedy introduced a parameter called critical velocity ratio in the critical velocity expression. So for the other canal, critical velocity is equal to 0.55 m y to the power 0.64. So this is the expression for the other canal system, where m is the critical velocity ratio and y is the depth of flow, and v naught is the critical velocity. So here for other types of canal, the critical velocity expression is 0.55 m into y to the power 0.64, where y is the depth of flow in meter and v naught is the critical velocity in meter per second. So v naught is the critical velocity in meter per second, and m is the critical velocity ratio. So m is the critical velocity ratio, that is equal to actual mean velocity to the critical mean velocity. So m is equal to, m can be written as v by v naught. The value of critical velocity ratio can be taken as, for different types of silt. For sand coarser than standard, the value can be taken as 1 to 1.2, and for sand finer than standard means 0.7 to 1. So now I am going to write the design steps of Kennedy theory. Design steps of Kennedy's theory. This is the channel. So the first step is assume a suitable value of y and compute critical velocity, that is equal to 0.55 m y to the power 0.64. Second step is compute the area of the channel. A is equal to q by v naught. Third step, side slope is taken as half horizontal is to 1 vertical and compute perimeter of the channel. Fourth step is compute hydraulic radius, hydraulic radius R, that is equal to R is equal to A by B. Fifth step, compute actual mean velocity by using the equation, by using the Chezy's equation or Manning's equation. So Chezy's equation, what is Chezy's equation? So Chezy's equation, V is equal to C square root of R into S, where V is the actual mean velocity, V is the actual mean velocity, R is the hydraulic radius, and S is the slope, bed slope. C is the Chezy's coefficient, C is the Chezy's coefficient, and Chezy's coefficient is computed by Cutter's equation. So according to Cutter's equation, the Chezy's coefficient can be computed as, according to Cutter's equation, C is equal to 23 plus 0.00155 by S plus 1 by N divided by 1 plus 23 plus 0.00155 by S into N by square root of R. So this is the Cutter's equation for computing the Chezy's coefficient, where S is the bed slope, and N is the Cutter's rugosity coefficient, and R is the hydraulic radius, and Ch is the Chezy's coefficient. So if I write the notation, so S is the bed slope, N is the rugosity coefficient, and R is the hydraulic radius. So with the help of this, we can compute the actual velocity, actual mean velocity, V is equal to 23 plus 0.00155 by S plus 1 by N divided by 1 plus 23 plus 0.00155 by S into n by square root of r into rs. Once we have computed the actual mean velocity, then we have to compare the value of this actual mean velocity with the critical velocity. So next step, if the actual velocity, this is step number 6, if actual mean velocity v is equal to the critical mean velocity, critical mean velocity v naught, then design is okay. Means whatever we have taken the trial depth, that is okay. So trial depth, so trial depth can be adopted, and with the help of this trial depth we can also compute the other parameters. But if v is not equal to v naught, so then we have to take another trial depth until v is equal to v naught. So there is a guideline to choose the trial depth. So guideline to choose trial depth. So that depends on the discharge. So if discharge and trial depth means y in meter. So if discharge is 0 to 20 meter cube per second, so we can take trial depth is 1 meter. Similarly 20 to 40, so we can take the trial depth is 2 meter. 40 to 80, then we can take trial depth as 2.5 meter. 80 to 100 meter cube per second, then it is 3 meters, and greater than 100 meter cube per second, then we can take trial depth as 3.5 meter. So this is the thumb rule. With the help of we can use this if the discharge is given, so with the help of this data we can start the trial depth from this value. Similarly the slope, if bed slope is not given, if bed slope is not given in the question, so we can take the bed slope as 1 by 3500 to 1 by 5000. In between we can take the different value of bed slope and try to uh, equate the actual mean velocity with the critical mean velocity. So this is the guideline for bed slope. So once again I am repeating the design procedure of the kinetic theory. Firstly we have to uh, take the initial trial depth, and with the help of this trial depth we have to find the critical velocity by using the equation v naught is equal to 0.55 m y to the power 0.64, where v naught is the critical velocity in meter per second and y is the depth in meter, and m is the critical velocity ratio, that is the ratio of actual mean velocity to the critical mean velocity. Once we have computed the critical velocity, so we can compute the area of the channel, that is by dividing discharge by critical velocity. And then if the bed slope uh, is not given, so we can take the 1.5 horizontal to 1 vertical and compute perimeter can be computed. Once we have computed the perimeter, so hydraulic radius can be computed, that is r is equal to a by p. And the next step, we have to find the actual mean velocity by using the Manning's equation or Chezy's or Cutter's equation. So generally we use the Chezy's equation, or generally we prefer the Chezy's equation as compared to the Manning's equation. So Chezy's equation is V is equal to C square root of Rs, where C is the Chezy's coefficient, R is the hydraulic radius, S is the bed slope. And this Chezy's coefficient can be computed by the Cutter's equation, and the Cutter's is given the formula to compute the Chezy's coefficient, that is 23 plus 0.00155 by S plus 1 by N divided by 1 plus 23 plus 0.00155 by S into N by S square root of R, where R is the hydraulic radius, S is the bed slope, and N is the rugosity coefficient. Then we have to find the actual mean velocity. If this actual mean velocity is equal to the critical mean velocity, then our design is okay, and trial depth is whatever we have taken the trial depth, that will be provided. If the actual velocity is not equal to the critical velocity, then we have to alter the depth, another trial depth we have to take, and the procedure is same procedure is repeated until the actual velocity is not equal to the critical velocity. So let us take the problem. The depth of flow in an alluvial channel is 1.5 meter. Depth of flow is given, that is y is equal to 1.5 meter, and critical velocity ratio is given 1.1, and Manning's roughness is given 0.018. So the critical velocity of the channel as per Kennedy's theory. So as per Kennedy's theory, V naught is equal to 0.55 m y to the power 0.64. So m is given, y is given, so we can compute the critical velocity, that is 0.55 into 1.1 into y is 1.5, so 1.5 to the power 0.64, so it will be 0.55 into 1.1 into 1.5 to the power 0.64, so it is coming 0.784 meter per second. 0.784 meter per second. So if I see the option, so B option is correct. Let us take the another problem. This is asked in Engineering Services Examination 1995. Calculate the bed width for an irrigation channel to carry a discharge of 5 meter cube per second. Side slope of the channel is R, half horizontal to 1 vertical. Assume critical velocity ratio as 0.8. And here the first trial depth is given 1 meter. If it is not given, so just by the thumb rule, that if the discharge is lies between 0 to 20 meter cube per second, so we can take the trial depth as 1 meter. And the bed slope is 0.2 meter per kilometer. And using Cutter's equation, B is equal to CRS, check the depth, take Chezy's coefficient is 30. So firstly, given data, discharge is given 5 meter cube per second, 5 meter cube per second, and the channel is trapezoidal, half horizontal to 1 vertical. critical velocity ratio is given, m is equal to 0.8 critical velocity, and the first trial depth is given 1 meter, and the side slope is 0.2 meter per kilometer, means 1000. So it will be 1 by 5000, and the value of c is also given 30. So step first, trial depth is 1 meter. So critical velocity ratio 0.55 m, sorry, critical velocity 0.55 m y to the power 0.64. So 0.55 into 0.8 into 1 to the power 0.64. So the velocity, critical velocity can be computed as, so 0.55 into 0.8. So it will be 0.44 meter per second. 0.44 meter per second. So first trial depth, that is y is equal to 1 meter, v naught is 0.44 meter per second. If this is the channel, and this is 0.5 horizontal, 1 vertical, and if this is y and this is b, so this is also 0.5 y. So here for first trial depth, that is 1 meter, the critical velocity we have computed, that is 0.44 meter per second. So once we have computed the critical velocity, so area of the channel can be computed as q by v naught, that is 5 by 0.44, so it is 11.36. Now in this channel, the side slope is given, that is 0.5 horizontal, 1 vertical, and depth of flow is y and bottom width is b. So area can be written as 1 by 2 into sum of parallel sides. So b plus 0.5 by 0.5 by, so it is y into y, that is 1 by 2, 2b plus y into y, and the area we have computed 11.36. So here 2b plus y into y is equal to 22.772. So 2b plus 1 into 1 is equal to 22.72. So b is equal to 21.72 divided by 2. So it is 10.86 meter. B is. So b and y is computed. So perimeter can be computed as, perimeter is computed. So perimeter is b plus 2 times square root of this value, this sloping side and this sloping side. So it will be y square plus 0.5 y square. So we can write 1 square plus 0.5 square, and b is 10.86 plus 2 into a square root of 1 plus 0.5 square. So value will be 10.86. 10.86 plus 2 times it is 1 plus 0.5 square. So the perimeter is 13.1 meter. So hydraulic radius can be computed as, hydraulic radius is a by p. So area is 11.36 divided by 13.1. So the value will be hydraulic radius 11.36 divided by 13.1. So it is 0.867. So 0.87 meter. So velocity can be computed as c square root of r into s. So V is equal to, C is given in the question 30. So 30 into square root of 0.87 into 1 by 5000. So actual mean velocity is 30 into square root of 0.87 into 1 by 5000. So it will be 0.395 meter per second. So this velocity is less than V naught because critical velocity is 0.44. So we have to uh, once again we have to take the depth. So trial depth can be reduced because this velocity is less than V naught. So second, let us assume the second trial depth. Let us take second trial depth, that is y is equal to 0.65 meter. This value is y, this value is b, this is 0.5 horizontal, 1 vertical. Now critical velocity, once again if I compute v naught, so 0.55 my to the power 0.64. So this value will be 0.55 into 0.8 into 0.65 to the power 0.64. So the critical velocity will be 0.55 into 0.8 into 0.65 to the power 0.64. So it is coming 0.33 meter per second. Second step is area. So area is Q by V naught. So 5 divided by 0.334. So it will be 14.97 meter square. This area can be computed as 1 by 2 into b plus y into y is equal to 14.97. So twice b plus 0.65 into 0.65 is equal to 14.97 into 2. So it is 29.94. So here divided by 0.65 minus 0.65 divided by 2. So the value of B is 22.7. B is 22.7 meter. So perimeter can be computed as so perimeter is equal to B plus 2 times square root of 0.65 square plus 0.5 into 0.65 square. So it will be B is 22.7. So 22.7 plus 0.5 into 0.65. So it is 0.325. So 2 into 0.65 square plus 0.325 square. So the value of perimeter is 22.7 plus 2 into square root of 0.65 square plus 0.325 square. So the value will be 24.15 meter. So the hydraulic radius can be computed as hydraulic radius is equal to A by P. So area is 14.97 14.97 divided by 24.15. 14.97 divided by 24.15. So it is 0.62 meter. So actual mean velocity can be computed as c square root of rs. The Chezy's coefficient is how much? So Chezy's coefficient is given, that is 30. So 30 into a square root of 0.62 into 1 by 5000. So the value will be 30 into a square root of 0.62 divided by 5000. So it is 0.334. 0.334 meter per second. So if I match the value of actual mean velocity with the critical velocity, so it is exactly equal. So step 6, V naught is equal to V. So it is okay. So provide depth y is equal to 0.65 meter. So this is the channel design as per the Kennedy's theory. B is equal to 22.7. B is equal to 22.7 meter, and the depth of flow is y is equal to 0.65 meter, and the side slope is 0.5 horizontal, 1 vertical. So this is the design as per Kennedy theory. So in the next class I will discuss the what is Garrett diagram, and then disadvantage of Kennedy's theory, and then I will discuss the another theory for the design of a stable channel, that is Lacy Silt theory. So take care of your health and happy learning.